Okay, so today's question is maximum spanning tree stability with the upgrades. So you are given an integer n representing n nodes numbered from 0 to n minus 1 and a list of ages where age is u, v, s and must, where u and v indicates an undirected age between node u and v, and given s gives the strength of the age, and must is an integer which is either 0 or 1. So the age must be included in the spanning tree with the must set as 1, and these ages cannot be upgraded. Okay, and you are given an integer k, the maximum number of upgrades you can perform. Each upgrade double the strength of an age, and each eligible age with must is equal to 0 can be upgraded at most once. Okay, so and what is the stability? So the stability of a spanning tree is defined as the minimum strength score among all ages in it, the minimum weight of the age, okay, among all the ages of a spanning tree. So we have to return the maximum possible stability of any valid spanning tree. If it is impossible to connect all nodes, we have to simply return -1. So you can see what the constraint is given for this instance. It's from 1 to 10 power 5. So let's get the use binary search here. So first let's define our left as 1. We can define right as maximum up to 2 into 10 power 5. 2 into 10 power 5, because if suppose a particular age is upgraded, so its weight can go up to twice. So the maximum value of the age we can get is 2 into 10 power 5. Now simply create a loop. So while left is then equal to right, we will calculate the mid value. Mid is equal to left plus right divided by 2. We can set a answer variable initially to -1. So set answer is equal to -1, and we will create a function can achieve. It will say whether a particular spanning tree exists as the stability as this mid value. So let's check if can achieve mid. We can simply set answer is equal to mid. Answer is equal to mid, and we have to find the maximum stability. So we will go towards right side of our array. So we will simply set left is equal to mid plus 1. Else if we can't achieve, we will check in the left half. So we will set right is equal to mid -1, and at last we can simply return answer. Now we have to create this can achieve function, but before creating this can achieve function, we will be requiring DSU. So let's try to write DSU code. So let's define class DSU, create constructor, take input the number of nodes given. So let's take it as n. Now we can define our parent list. So self dot parent is equal to, each node is the parent of itself at the starting. So set I for I in range n plus 1. Similarly, let's define the size array. So self dot size, each node has a size of 1 at the starting, so we can simply set as self dot size is equal to 1 for I in range n plus 1. We will also keep the track of how many different components are there. So we can set it as n because there are n nodes and none of the nodes are connected to each other at the starting, so there are n components. So let's set that self dot components is equal to n. Now as we know, the DSU contains two functions, find parent and the union. So let's try to create a function find parent. So define find parent. Find parent will take a node value for whichever node we want to find its parent. So suppose if node is equal to self dot parent of node, that means it's the root, means it's at the top, so simply return the node. And And if it's not the case, we will simply set self dot parent of node is equal to, we will call this function recursively, so self dot find parent, of which parents we want to find, this one, self dot parent of node, and at last we can simply return self dot parent of node. Now our find parent function is completed. Let's try to create now union function. So define union self dot, it will take two nodes u and v. Now we will find the what is the ultimate parent of u. So ultimate parent of u is equal to nothing but we will use the function created above, self dot find parent of u, and similarly what is the ultimate parent of v, we can simply find self dot find parent of v. Now we will check if ultimate parent of u is equal to ultimate parent of v. That means they are already a part of the same component. We will simply return false, no union needed here. And if it's not the case, we will check if it's not the case, we will simply say which size is greater, if it is of ultimate parent of u or ultimate parent of v. So let's do that. If self dot size of ultimate parent of u is less than self dot size of ultimate parent of v, we will always add the smaller size in the larger size one. So if self dot size of ultimate parent of u is less than self dot size of ultimate parent of v, then self dot parent of ultimate parent of u is equal to, we will set it as ultimate parent of v, and the size of ultimate parent of v will increase. So self dot size of ultimate parent of v plus is equal to self dot size of ultimate parent of u. Now if it's not the case, either it is equal or size of u is greater than that of ultimate parent of v, we can simply do the reverse of this. So self dot parent of ultimate parent of v is equal to ultimate parent of u, and self dot size of ultimate parent of u will increase self dot size of ultimate parent of v. And after doing that, of course the this thing self dot parent of ultimate parent of u, it's correct, we will set it to self dot ultimate parent of u, and self dot size of ultimate parent of v will be nothing but, so after doing this union, what will change, the component size will decrease, self dot components size will decrease because we have done the union, so the component size will decrease by 1. So components minus is equal to 1, and finally we can return true for this, that union has done successfully. So we have created this DSU class code. Now we will try to create this CanAchieve function which will make use of our DSU. So simply create CanAchieve function, define CanAchieve. CanAchieve will take the input, the stability which we have passed as made in the below code. So first we will create call the class. So DSU is equal to DSU of what is the number of nodes, it's nothing but n. Okay, and you can set as upgrades is equal to, we can set upgrades as equal to 0. Now let's go one by one. First case is what if the must is set as 1. So let's code for that. For u comma v comma small s comma must in ages. Suppose if must is equal to 1, and if the age is less than the capital S, then of course we will return false, because stability is nothing but the minimum age among all the ages, but we have found a age which is minimum, that particular S also means this stability with this capital S is not possible, and we will simply return false. What else we can be the case? We will take the cycle. If not dsu dot if not dsu dot union, you come, if we are unable to do the union between u and v, that means they are already a part of the same parent, and if we do the union between u and v, then it becomes a cycle. So in that case also we can simply return false. So it is the case for if the must is set as 1. Now let's check another case for u comma v comma s comma must in ages. Suppose if S is greater than or equal to capital S, that means we can take this as a part. So first thing we should take, the must should be equal to 0, and S should be greater than or equal to capital S. It means it is greater than or equal to the minimum value, we can take this part and simply do the union. So dsu dot union, and what union we will do, just two nodes u and v. Okay, and now the last one. So for u comma v comma s comma must in ages, if must is set as must is equal to 0, and of course s is you can say as less than the capital S, and 2 is times the S is greater than or equal to capital S, then only this thing works. So what we will do, first we will check if they are not the part of the same parent. Okay, they are not under the same parent. So if dsu dot find parent of u is not equal to dsu dot find parent of v, then only we will go on and we will check if the upgrade has exceeded the k. If upgrade is greater than a k, then we can't do more upgrades, so we can simply return false here. And if that's not the case, we can simply do the upgrade. So we will create a union. So dsu dot union, and we will create a age between u and v, and we have used the one upgrade, so we can simply increment the upgrades count plus is equal to 1. And finally we have to check whether we have created a spanning tree or not. If the number of components is equal to 1, that means we have created a component. So simply return self dot it's not self dot, actually it's dsu dot components, dsu dot components. If dsu dot components is equal to 1, means we have created our spanning tree. If it is not equal to 1, means the spanning tree does not exist. So let's try to run and check if this works. Okay, so we are getting some error, invalid syntax, self dot find parent. Okay, yeah, in place of comma by mistake we have put dot. So try to run again and check. Again some error. Let's sort out the must is equal to in place of and by mistake in place of d we have put as, so set is at and. Let's try to run it again and check. Seems another mistake, same issue again, in place of and mistakenly answer. Let's try to run again. List object is not callable. We are getting some error. List object is not callable. It's a list. Now we have defined it in the parenthesis in place of the big bracket. Okay, so we have set this up. Let's try to run again. Now we are getting the wrong answer. Try to figure out what's went wrong in our code. Let's try to go from top and check. So let's try to code check this. So we have defined dsu, we have set the parent correctly for I minus 1, and then we have size also, we have set the components to n. Now we have created a find parent. So if node is equal to self dot parent of node, we have return node, correct. If self dot parent of node is equal to self dot find parent, self dot parent of node, we have done this correctly, and last we have returned the self dot parent of node, that's also correct. Now if we go through the union function self dot u comma v, we have found the find parent of u, find the parent of v, and we have checked if ultimate parent of u is equal to ultimate parent of v, we have returned false correctly. Now we have checked if self dot size of ultimate parent of u is less than self dot size of ultimate parent of v. We have simply called self dot ultimate parent, self dot parent of ultimate parent of u, set is as b, it's also correct. Self dot size of ultimate parent of v, we have sum it with the self dot ultimate parent of u, that also seems correct. Now for self dot parent of ultimate parent of v, we have set it as u, okay, and self dot size of ultimate parent of u, we have simply we have missed the equal sign here, we have just missed the equal sign here. I think this was only the issue. Let's try to run and check if this works now. Again there is a wrong answer for the same one. So I think the same mistake we have done somewhere else also. Let's check that. So self dot size of ultimate parent of u plus is equal to self dot size of ultimate parent of v, that seems correct, and self dot components minus is equal to 1, and finally we have returned true. Now let's check our this can achieve function. So we have called for dsu of n, upgrades we have set as 0, and for v comma s comma most in ages, we have checked if most is equal to 1, and s is less than s, simply return false, and if not dsu dot union u comma v, we return false. This also seems correct. Now for u comma v comma s comma most in ages, if most is equal to 0, correct, and s is greater than or equal to s, means we can simply do the union. So this also seems correct, dsu dot union u comma v. Now for u comma v comma s comma must in ages, if must is equal to 0 and s is less than s, oh, here in place of s we have written 2 into 2 in place of 2 power 2, just a typo mistake. Let's try to run and check now. Yeah, so our test cases has passed. Let's try to submit and check if this works. So many typo mistake. Yeah, so our code has passed successfully. Thank you for watching.